Hello, everyone. Thank you for coming to this CopView event. And today we're going to talk about the ocean and climate change. And for me, the ocean and climate change are very much linked. I'm a marine biologist and I used to study coral reefs. I still do sometimes. And I used to teach students how to study coral reefs, how to monitor them, how to treat them, and how to look after them. However, about 2 years ago, I actually quit my job because I realized that we are in this decisive decade where we have to make sure that our emissions go down and that action is taken on a social and political level, and that just teaching my students how to monitor coral reefs is not going to get them a job looking at coral reefs and taking care of them, because we are losing them to climate change. I think most people know that coral reefs are impacted by climate change, but all the other impacts on the ocean are very unknown and hardly spoken about. And that's what today's event is about, that we talk a bit about what is happening to our ocean, because in the end, our ocean is 70% of our planet. If you look at our planet from the satellites or from the space, it is blue, it's not green. So the ocean should actually play a really, really big role, because it does play a really big role in our planet. We're going to start off with a presentation by Dr. Ray Schmitt from the WHOI Oceanographic Institute in the US. And then I'm going to show you a short video by Kleinworks. And after that, we're going to have our first discussion round where you can ask questions and we can discuss what we just heard together. So Ray, if you're ready, you can take the stage.
Thank you. Yes, hello everyone. I would say good morning because it's still morning here in Woods Hole, but I realize it's the evening over in Europe. So today I'm talking about the ocean's role in climate, and as we're calling it, the elephant in the climate room. I like to quote Arthur C. Clarke from an article he wrote in Nature in 1990, how inappropriate to call this planet Earth when clearly it is ocean. As Fran just mentioned, the oceans cover 70% of the globe, and it is the blue planet, it's not the green planet. That dark blue ocean absorbs a lot of heat and actually takes up most of the solar radiation incident on the planet. All that water also has 1,000 times the heat capacity of the atmosphere, and 100,000 times as much water as the atmosphere, and 97% of all the free water on the planet. So it's obviously very important to the climate system, yet it's been neglected. It dominates the Earth's budgets for heat, water, and carbon, and it's been neglected in climate studies. And today we're going to review the role of the ocean in the climate system, how climate change is affecting the ocean, how the ocean has protected us from some of the effects of climate change, and may provide a solution to the carbon and food problems humanity faces. So, as I mentioned, the oceans have over 1,000 times the heat capacity of the atmosphere, 100,000 times as much water, and 50 times as much CO2. I'm going to talk about each of those three things, heat, water, and carbon in turn. And the Earth's heat budget is dominated by the ocean. And this figure shows in red the areas where the ocean is absorbing heat from solar radiation. And the blue areas are where the ocean is giving up heat to the atmosphere. You can see the tropics are where the ocean gains a lot of heat. And the extratropics, especially off the western boundary currents, off the Kuroshio, the Gulf Stream region, are where quite a bit of heat is given up to the atmosphere. And the ocean and atmosphere together have to transport that heat from the tropics to the poles, because the radiation to space tends to be rather well uniform, but we need to get all that heat from the tropics to the poles, and only the ocean and atmosphere can do it. The land's role in the heat budget is rather modest. It absorbs heat during the day and releases it at night, and has no method for moving it around like the ocean and atmosphere do. So in transporting heat from the tropics to the poles, the black line is the total amount of heat that has to be transported, and there's a complex interplay between the ocean by itself, just the heat, sensible heat content of the ocean as it moves it around, the currents move it around, is in blue, but there's also an ocean atmosphere latent heat flux. That is, the atmosphere, water evaporates from the ocean, that's energy put in from the sun, and it goes into the atmosphere, and then it rains out at a different latitude, and that's part of the water cycle. But it always has to return to its point of origin in the ocean. Otherwise, sea level would be changing by many meters per year. So it's really a two-component system, the ocean and the atmosphere, all this water vapor that's transported. And then the dry atmosphere itself, because air moves pretty fast compared to the speed of water in the ocean, has a fairly large sensible heat flux as well. And in total, they amount to nearly 6 petawatts at mid-latitude. I like to show how the heat gain from the sun, we call it the net shortwave gain, is 165 watts per meter squared averaged over the ocean. The sensible heat loss, just because the ocean is warmer than the atmosphere, you have very modest 10 watts per meter squared flux due to the temperature difference. But it's really the latent heat flux of evaporation that provides most of the energy from the ocean to the atmosphere. And then there's also long wave radiation that is intermediate there, about half as much as the latent. And the important thing about this plot, when you talk to meteorologists, they like to say that the atmosphere drives the ocean. I think that's a big mistake. I think it's really the ocean that drives the atmosphere, because it's this latent heat that provides moisture to the atmosphere, and that's the energy for hurricanes, for storms. So in my mind, the sun heats the ocean, and the ocean gives some of its heat to the atmosphere to drive the atmosphere. We know that temperatures are rising over ocean and land. And of course, the consequence for that is sea level rise. And we know that the ocean has absorbed over 90% of the heat of global warming. This has delayed the full impacts of CO2 warming for several centuries, but at the cost of sea level rise and increasing stratification. As you warm the upper ocean, the density contrast with deeper layers increases, and so it's harder for the ocean to mix, harder to get nutrients into the euphotic zone to maintain ocean productivity. And the other thing, of course, is that these rising temperatures lead to more evaporation and a changing water cycle. So now I'll talk a little about the water cycle. And this has always bothered me for a long time. If you Google global water cycle, do an image search, you'll find that most of them only have a very small ocean in one corner of the diagram. And this is, a complete corruption of what the picture actually is. If you look at where most of the water is, of course, 97% of it's in the ocean, about 1% is in lakes and rivers on land, and about 2% is tied up in the ice sheets on land and in the ocean. Ocean evaporation dominates the source of moisture to the atmosphere. It's 85%. Ocean precipitation dominates as well. And only about 10% of ocean evaporation ends up cycling through rivers. So I have a different water cycle picture. This is the Oceanographer's water cycle, and it shows big return flows in the ocean. That is, we're talking about meters per year of evaporation in the subtropics, and that water has to be returned through the ocean. So that's part of that ocean atmosphere water cycle that I mentioned. Now, the patterns of evaporation and precipitation are shown in this figure that we did about a decade ago. The red areas are areas where water is leaving the ocean, evaporating from the ocean. And you can see it's each of the subtropical gyres. The part where the zero net evaporation precipitation line pretty much defines the subtropical gyres, at least in my mind. And so that's areas where salinity tends to be higher. The blue regions are where precipitation dominates. And of course, those areas tend to get fresher. We also have a lot of rainfall in the intertropical convergence zone at low latitudes. So this generates a kind of interesting pattern of meridional transport by the ocean and atmosphere, and they complement each other. This is a figure that we've developed showing the atmospheric transports. This would be transport to the north. We've lost the figures, the numbers here, but it's in Sverdrups. And, you know, you're talking about 2.5, maybe almost 3 Sverdrups at mid latitudes of water transport. And there's 2 lines here. The dashed line is what we expect it to be in 2100, comparing with the solid line of our estimate for the year 2000. So quite a bit of increase in transport. And of course, the cause of this is the fact that warm water evaporates more readily into a warmer atmosphere. And this is just the property of the water molecule. The vapor pressure of water is a function of temperature. And the average temperature of the planet is about 15 degrees C. And for every degree increase, you get about a 7% increase in the moisture carrying capacity of the atmosphere. So an enhanced water cycle will change the distribution of salinity in the upper ocean. And this has been observed. And in fact, a change in the water cycle has been very difficult to document on land, mainly because mankind is pumping up groundwater for irrigation, damming rivers for power. We've really interfered greatly with the terrestrial water cycle. And so it's hard to tell what the natural variability is. But if we looked at salinity changes over the past 50 years, you can see that the salty areas, such as the North Atlantic and South Atlantic, have gotten saltier by about 0.2. So it's possible to find salinities in the salinity maximum of the North Atlantic of 38 parts per thousand. And other regions, such as the North Pacific, have gotten fresher by about 0.2. So these are pretty big changes, and they're well documented in the ocean and provide the best evidence for a changing global water cycle. Now I wanted to talk about the carbon cycle. This figure shows, this table shows the reservoirs of carbon dioxide in the atmosphere. You can see the ocean dominates by far, and there's some estimates of the rate of change in gigatons of carbon per year. The oceans have most of the carbon, quite a bit more than the atmosphere. And these are some of the estimates for what's available in fossil fuel reserves and which way it's going. So the oceans, again, the elephant in the climate room for carbon. And if we look at past climates, we find a strong correlation between the global surface temperature and the CO2 in the atmosphere. They've gone up and down together as the ice age has waxed and waned. And we see this alarming increase to over 400 parts per million in today's atmosphere. And the temperature has yet to catch up because of this, the couple of century delay that the ocean's giving us. It can absorb so much heat because of its vast heat capacity, and it is absorbing over 90% of the heat of global warming. So the temperature's not quite cutting up to the CO2, but we can see that there was this variation. And where did that CO2 go in the ice age? It went into the oceans. And so an interesting question is, can we get that CO2 back in the ocean to avert the worst effects of global warming? So some of the consequences of CO2 warming for the ocean. The warming ocean, of course, leads to sea level rise just from thermal expansion. It's also causing less vertical mixing, which will inhibit biological productivity, and it's causing more evaporation. And this more evaporation leads to stronger storms, more intense hurricanes, more water transported onto land for terrestrial storms, and an intensifying water cycle, which means the wet get wetter, the dry get drier. And we've seen this in the ocean patterns. The salty areas are getting saltier and the fresh areas are getting fresher. So, some regions such as the Western US could be in for a long-term drought, whereas in the East, we seem to be getting more and more floods and more intense floods. I mentioned the increasing stratification and decreased mixing that inhibits both the CO2 absorption and lowers ocean productivity, which is an adverse feedback on the CO2 system. But today we're going to talk about how the oceans could well be the solution to the CO2 problem. If we increased ocean CO2 content by only 2%, it would take up all the anthropogenic CO2 we've emitted and sequester it for thousands of years in the deep sea. One way to do that might be fertilization of the subtropical oceans, which could provide an important protein source for an expanding human population. This is a quote I've taken from a recent paper of mine. With 50 times as much carbon, 1,000 times the heat capacity, 100,000 times as much water as the atmosphere, the ocean clearly plays a central role in the climate of our planet. Yet the Paris Climate Agreement has only one mention of the word ocean in connection with ecosystems. One might think that we lived on an oceanless planet for all the attention it gets. And my article, which is in Oceanography magazine, it's called The Ocean's Role in Climate, concludes, it's the ocean, stupid, which is, it comes out of American politics. Anyway, there's a reference to the paper, and I would be happy to take any questions when we get to the discussion session. Thank you very much.
Thank you, Ray. That was really, really interesting. And I think you gave us a great overview of what the ocean is doing and how it interacts with our climate and with our atmosphere. Next, I want to show you guys a little video from Climate Works that shows how the ocean could take up some of the carbon that is already in our atmosphere or that we are still pumping out there. Before showing you the video, I want to make sure that you all understand that this is not the solution that will help us solve all our climate problems. In my opinion, and this is literally what we need out of a scientific perspective as well, we have to decarbonize as fast as possible. And that is a really big priority. And we also have to make sure that the communities impacted by climate change have the means to adapt to what is happening where they are. But next to that, we also need to take some of the carbon that is already in the atmosphere out, because otherwise we will never stay below 1.5 degrees or even below 2 degrees. So this video shows how we can do that without going into talking about actually reducing fossil fuels or doing adaptation, which are also really, really important. And it's not meant to take them away, it's just meant to show one part of the 3 actions we have to do.
We have built a globalized economy based on fossil fuels and added 555 billion tons of CO2 to the atmosphere. The ocean has absorbed more than a quarter of this carbon, thereby increasing seawater acidity by 30%. Land is also a significant carbon sink. However, half of our CO2 emissions remain in the atmosphere, causing a carbon traffic jam that's pushing our climate towards dangerous new conditions. This CO2 must urgently be removed, and the ocean, with its enormous volume and natural carbon pumps, might provide the key. CO2 diffuses into the surface layer of the ocean whenever it is more abundant in the air than in the water. Once dissolved, powerful carbon pumps remove CO2 from the surface, pulling yet more of it into the ocean. Ocean currents move CO2-saturated surface waters poleward, where they cool and sink, pulling our emissions into the deep ocean, where they can remain isolated for thousands of years. Over geologic timescales, weathering of rock washes alkaline molecules into the ocean, thereby converting dissolved CO2 into bicarbonate and carbonate forms. This natural alkalinity allows the ocean to take up more CO2 without further increasing ocean acidity. On much shorter timescales, primary producers photosynthesize, using sunlight and nutrients to turn dissolved CO2 into organic carbon that fuels the food web. As organisms feed on one another and trillions of microbes digest even the smallest of particles, most organic carbon is rapidly recycled back into CO2. However, a small fraction of organic carbon escapes the food web and is sequestered in the ocean. This includes organic matter that sinks into the deep ocean or is structurally so complex that it becomes inaccessible to microbes and is sequestered in the ocean for thousands of years. Organic carbon also gets trapped in coastal soils by salt marshes, mangrove forests, and seagrass meadows. Alone, the ocean's carbon pumps are too slow to reverse climate change. However, with research and innovation, we might be able to give these natural pumps a boost and avert the worst consequences of climate change. For example, large-scale seaweed farming or ranching of free-floating sargassum can remove the carbon stored in plant biomass by putting it to the ocean floor or by locking it up in long-lived nutrient poor waters. The export of carbon to the deep ocean could be boosted the growth of seaweed. Protecting and restoring blue carbon ecosystems would prevent emissions associated with ecosystem degradation and can increase storage of organic carbon in marine soils. Ocean alkalinity can be enhanced in a number of ways, thereby increasing the ocean's absorptive capacity for CO2 and counteracting ocean acidification. Proposed approaches include the direct addition of alkaline minerals to beaches or the open ocean, accelerated weathering of limestone or silicate rock in controlled reactors or electrochemical seawater treatment facilities. Finally, liquid CO2 from emissions captured on land could be stored in subsurface geological formations or in the deep ocean. It has even been proposed to increase water density at the poles to accelerate the downward transport of CO2 to the deep ocean. Some of these approaches might have a real shot at sequestering billions of tons of CO2. Their evaluation, in terms of efficacy, environmental impacts and cost, field testing and potentially large-scale deployment will require multi-sectoral collaboration, innovation, and an enabling governance system. Join the conversation at oceancdr.net.
So now I want to hear if any of you have any questions for Ray or about the video we just showed. And if not, I have a few discussion topics we could talk about. James?
Thanks, Ray. That was a really interesting talk. I wondered the mention about the ocean and ecosystems in the Paris Agreement. What was the mention that they did include?
Oh, I don't recall. It just something about how ecosystems might be affected by the changing pH of the ocean, the changing alkalinity. But they've completely ignored the heat absorbing capacity of the ocean. It's just remarkable that they've pretty much ignored it when it covers 70% of the planet. I think.
Question from Ruth?
Yeah, I mean, this is all very alarming, isn't it? But so does the UN actually know about this? How many scientists are telling them about this?
Oh, I know there are committees. I think the problem was with the Paris Climate Agreement. I think you mostly have politicians there. Here in the US, it's been a long fight. The meteorological community is very jealous of its hold on the climate topic. And they've been reluctant to cede any interest or any ground to the oceanographers. So my whole career, I've been fighting this fight. Those pictures, I've been studying the global water cycle, and there have been many national initiatives on the global water cycle that ignore the ocean, and it drives me crazy. So it's just one of these things we have to continue to fight.
Yes, and I think another problem is that science in the ocean started much later than science on land. So we are always catching up to even know enough about the oceans. And it's just a lot harder to do science in the ocean. Like, you want to take pictures, you need an underwater camera, all these things. The deep ocean is extremely hard to study because you need very expensive equipment and you need expensive boats to go out there, while getting on top of mountains and other things is actually a lot easier to do. So there's also the factor of us not knowing as much about the ocean as we do about the land and maybe even the atmosphere, which may also hinder then for all that information to get to the UN and to the politicians. But the UN is now having an ocean decade, so hopefully they are changing what they know about the ocean during this decade, because they're putting now an emphasis on the ocean.
Yes, I mean, one of our problems in oceanography is the lack of long records. On land, you got many cities which hundreds of years of temperature and humidity and pressure observations. But in the ocean, we're lucky if we have 50 years. But things like the Argo float array have really helped with understanding how the ocean is absorbing heat from the sun. And so our global observing system, which is another topic I've done a lot of work on, has really helped in the past, say, 20 years. And of course, now we have a lot of satellites up there looking at the ocean for even things like salinity. So we're starting to catch up, but yes, we did start from a deficit. We were way behind.
And
how quickly are we losing ice from the North and the South Pole? And what effect will that have on our, sort of measurements of the water measurements and also the acidity of the ocean? And how is the ice, how does it affect the, when you said about the ice helps to, not just to cool the system down, but to actually alter the pH or whatever of the system. I don't know whether I'm coming over not quite sensible as I'd like to be, but I'm worried about the shrinking of the Arctic and the South and North Pole.
Yes, diminishing sea ice, which has been very well documented by the satellite observations. It causes a positive feedback for warming because the ice reflects most of the solar radiation, whereas the dark blue ocean absorbs the solar radiation. And if you have less ice, you get more warmth during the Arctic summer put into the ocean. And so then it's harder for the ice to grow back. So it's, if you lose some ice, you're going to lose more next season. So the ice is disappearing. That's warming the high latitude ocean. And that it may allow more CO2 absorption in the high latitude ocean. I'm not sure about that. If more surface area of the ocean is exposed, at least for the summer. And of course, one of the consequences of CO2 absorption is a change in the pH. It's becoming more acidic, or really less alkaline. And there's a concern of what that will do to biological systems. Now, I think later on we're going to hear more about the possibility of sinking sargassum and other seaweeds into the deep ocean. And I think that would be a method that would have less impact on the upper ocean pH than simply letting the CO2, increasing atmospheric CO2, increase the pH of the upper ocean. If you get it into the deep ocean, it'll stay there for thousands of years. Some of it will work its way into the sediments. And we could even think about burying things like sargassum in the deep ocean. But I'm no expert on all those topics, and I'm happy to listen to the conversation.
Oh, thank you.
Mar, you got something to add as you've been to the Arctic a few times?
Yeah, I can add something about the Arctic sea ice. So it's actually decreasing way faster than any of the models predicted, which is very troubling. And I think the latest predictions say that we will have Arctic-free Arctic in summer by 2035 or something like that. So really, really early. In winter, we will always have a little bit of ice formation again, but the problem is that in summer, we don't get enough sea ice. And so this is affecting the entire ecosystem, basically, because the algae that grow in the sea ice are key to the maintenance of that ecosystem. And so if the sea ice disappears, then the Arctic ecosystem will basically completely change and become a different ocean, basically. Yeah.
Kathy, you had a question as well?
Yeah, hello. First of all, just to say thank you very much for the presentation, which was very interesting and excellent. Thank you. And also the little film. Now, my question, I apologize if I don't articulate it very well because I'm not very familiar with all the science involved. But I was just wondering, all these methods for potentially storing carbon in the ocean, presumably at the moment, these are sort of untested and theoretical. Is that right? And
Yes.
Locally to us in the northwest of England, we have plans. There are plans to build this massive hydrogen production unit, and apparently they're going to store the CO2 under the ocean. Now, I'm not sure, is that a slightly different thing? Are they talking about, when they talk about carbon capture and storage, does that basically mean capturing the CO2 in a container and sticking it under the ocean? Or are they talking about some of these methods that you mentioned in the film, the seaweeds and alkalinization and then deposition of the CO2 into the deep ocean? Are they different things, or is this the same thing? I'm just trying to understand a bit more about the process of this massive plant that is going to be built near us that seems to be a not very good idea. And I've been reading about how actually it could actually make matters worse with increasing amounts of CO2 produced rather than being a source of clean energy. Thank you.
Yes, so I think these machines that are now slowly popping up in places, I know they have made one in Iceland. They are taking the CO2 straight out of the atmosphere or straight away from the fume stocks of actually when you're burning fossil fuels. So they take it out of the atmosphere. So it's not the same as alkalinity enhancement or growing seaweed. But then if they want to store it in the deep ocean, instead of pumping it into rock, they will pump it to the deep sea or into the sediment. And I actually don't know exactly how they want to do it, but apparently maybe they need a big pump, or maybe, as you said, they will put it into some kind of container. But Mar, do you know how they will do that?
Yeah, so I'm not sure exactly about the one that you're talking about, Katie, but there are plans of putting together hydrogen production with ocean alkalinity enhancement. So on the process of creating the hydrogen fuel, you have some of these extra molecules that could be delivered to the ocean to enhance alkalinity and therefore enhancing the capacity of the ocean to absorb CO2. Then so this is completely different from direct air carbon capture, which is what Fran was talking about. And that, I think, when they talk about storing the CO2 in the seabed, they are mostly talking about pumping it like in a liquefied form into the empty caves or whatever you want to call it, where there used to be oil or gas or whatever, and that's where they pump it in, kind of back from the atmosphere there. So it's not, they don't put it into barrels or anything. They pump it in a liquefied form back into the aquifers where there used to be oil or gas.
Yeah. And there's oil companies who use that same method to pump in the CO2 into their places where they had oil, and it actually helps them extract more oil as well. So they call it a very green thing, that they are actually taking the CO2 that they're producing out, but at the same time, it helps them get more oil out of their wells that normally wouldn't be able to get there. So it's definitely a bit of greenwashing going on right there. I don't see any questions, so I would like to get to the second part of our talk. And for that, I want to introduce you to Sargassum, which is an algae that is very special and that has been kind of changing in the last few years of how much of it we had. And I just want to show you guys a few short slides to give you a bit of a picture of what kind of algae it is. And then I'll give the microphone to Jorge and to Mar to talk about the projects they are working on with this algae. So the algae we are talking about today is Sargassum, and there's over 350 species of it, but we're only talking about 2 species, which are pelagic Sargassum. So they never attach to the ocean floor like normal algae, but they actually live the whole life at the surface of the ocean and also grow there by making duplicates of themselves. And that's what the algae looks like. So it's really pretty, and it has these round bubbles that make it float. Here I want to show you what has happened with this algae in the last 10, 11 years. So you can see every summer there's a huge influx that goes all the way from Africa to the Gulf of Mexico. And you can see now the last year in this graphic, 2018, had a really, really big influx right here. And you don't see 2019, 2020, 2021, but 2021 was very similar to 2018. And even though there's a flux of how much there is each year, in general, there is a bit of an increasing trend of having this algae in this belt. But this belt has actually only existed since about 2011. Before that, there was no Sargassum algae found in this belt. So this is a very new thing. And what science has found out so far is that the Sargasso Sea in the middle here, it's in the middle of a gyre where all the currents get together, and it's called the Sargasso Sea because the Sargassum is living there and has been for forever. There's reports from Christopher Columbus about the Sargassum there. There's even reports from when we thought the Earth was flat that there's a big patch of algae at the end of the at the edge of the sea that they thought was like the edge of the world. But in 2019, 2010, there was a very extreme northern Atlantic oscillation, actually the most extreme we've ever had, which meant that winds and surface currents were able to push some of that sargassum out of the Sargasso Sea, and a very small patch, or not very small, but a smallish patch started accumulating in North Africa on the coast, and then it got pulled down into the Atlantic, into the tropical Atlantic, and there it had very good conditions. So tropical Atlantic is a lot warmer than the Sargasso Sea. It also has upwelling, so there's a lot more nutrients. And of course, algae, they photosynthesize, so having a lot of heat and also having a lot of nutrients makes them grow. And when Sargassum has good conditions, it can double in 11 days. So a small patch can become a really big patch very fast. And then in summer, the equatorial currents are pushing the Sargassum towards the shores, both in Africa and towards the Caribbean. And on the way there, you have several rivers that have outflows, such as the Amazon, the Orinoco, and the Congo River, that add a lot more nutrients again, helping these algae to proliferate and to really grow a lot. And of course, all the different countries have also land runoff that helps that too. So what we have now is a situation where we have this belt that has been established and is likely not going to go away. It has been established because of changes done to our ocean and to our climate, and also because of all the runoff we have from how we are treating our land masses. So it is very much a problem that has been started because of us humans. But the really exciting thing about the Sargassum is that it likely is caused by climate change, at least partially. But in my eyes, it's also a really strong way of solving the climate crisis and drawing down carbon. So it's one of the few things that is caused by climate change, but can also be a solution to climate change, which is really exciting. And that's what Jorge and Mar will be talking about next. So Jorge, if you would like to start.
Absolutely. Thank you so much for organizing this event, and thank you for all the distinguished panelists, as well as the people that are tuning in from all around the world. My name is Jorge Vega. I am the head of communications and public affairs for C Combinator. We are a public benefit corporation that started last year. In what we're aiming to do is exactly what Francisca just mentioned, is we're facing a very big issue with Sargassum, and we're really aiming to turn it into an opportunity. We're doing that really, and as a public benefit corporation, in case that you don't know, it means that we are legally mandated to have some sort of social impact. In our case, it's established as helping restore oceans and other types of ecosystems. And Sargassum presents a very unique opportunity because it is a very versatile organism. Right now, it's very exciting to be in a time where we're exploring what I call the humble organisms like mycelium, mushrooms, lichens, seaweeds, all these things that people thought were boring and maybe even a little bit scary. Now we're understanding that they're actually very, very important parts of ecosystems around the world. And seaweeds, and especially Sargassum, seems to be like that. But also in the Caribbean, it's interesting because there's never been, unlike other regions in the world, a very traditional culture or aquaculture around seaweeds. So we're also very excited that knowing that under climate collapse, the Sargassum explosion has been created, but then it's also presenting an opportunity for not only new ecological solutions, but also new socio-economic solutions that we're going to be facing to even right wrongs from the past. In this case, supporting a much stronger local or regional circular economy in the Caribbean. What we're doing at Sea Combinator is that we are essentially taking the Sargassum, we're picking it up before it rots. And this is also very important because like it has already been established, the seaweeds, the Sargassum essentially captures the CO2 from the water. It's a filter, it's cleaning it up. But if you let it rot, it releases a lot of those things. Not only that, but it's also very toxic. So as it accumulates in shores, it kills fish stocks, it kills coral reefs, and it affects the livelihoods and the quality of life of people living in the coast. So what we do is that we try to get in very early. We pick it up before it rots, essentially avoiding it from rotting and re-releasing that CO2 and all those toxic emissions. And we're turning it into a variety of products. Primarily, we're focusing on 3 right now: an organic fertilizer, vegan leather, and bioplastics, and also emulsifiers for vegan cosmetics. I can show you some of a little bit of what we're doing with the biostimulants, because I also want you to get sort of like a very, an actual visual proof of how amazing Sargassum is. Please let me know if you can see my, there you go. So like I said, we're focusing on sort of creating products that are low carbon and made from complete biomass. This is also very important, right? Because a lot of the issues that the ocean is facing, sadly, everything ends in the ocean, the good and the bad. And as you all know, there's an increasing and very concerning amount of microplastics. Plastics basically start degrading until they form these microparticles that we're finding everywhere. So we're also very excited about doing things that are just low carbon, because they are avoiding, essentially, they're replacing things that are made with high fossil fuel content or that require a lot of energy expenditure, but also things that are marine biodegradable, meaning that if they end up in the ocean, as they often do, they won't really degrade into these microplastics. We're seeing a lot of Sargassum. This is the way that it accumulates, in case, a lot of people see these photos for the first time and they really don't believe the scale. And this is, some of the people here in the call might attest, this is nothing compared to some of the things that we're seeing across the Caribbean. So it's not, it's not surprising that people in the past potentially saw these huge mats out in the middle of the Atlantic, and now this is even worse. It looks like continents of it. So what we're doing is that we're essentially in 2 locations. We're in the Yucatan Peninsula in Mexico on the southern part, which is Quintana Roo. And that's where a lot of the Sargassum ends up floating into throughout the Caribbean. So we're picking up the Sargassum, we're cleaning it up. And from that, we're creating the first product that we're doing, which is this organic kind of biostimulant or fertilizer. We take it to the plant, it's fresh, we're cleaning it off to take off any impurities and the salt. We extract it. And then with some very basic modifications, we're using this, and basically it's ready to go to apply to fields. What is amazing about Sargassum and other seaweeds is that they contain phytohormones. They're natural hormones. And if you think about it, it's very interesting, right? Seaweeds are some of the more resilient plants out there, and especially Sargassum. It's just floating around, no roots, doesn't have to be holding on to anything. It's just taking all the nutrients that it can and all the sun that it can, and it's exploding. And so essentially these phytohormones, which are natural hormones, when you apply it to other plants, it's signaling to these plants to gain a little bit of that resiliency as well. We've been seeing a lot of amazing results from this. This is from one of our tests in India, where we've seen, as high as 45% increase in yields compared to traditional fertilizers, as well as other stimulants made from other types of seaweeds. So this is also very, very exciting, again, because if we look at it in terms of the tropics and coastal economies are the first ones to be affected by climate collapse. And if people in the Caribbean are already going through a lot of volatility, which limits their ability to be food self-sufficient, then we're able to take essentially what is created regionally and process it for the betterment of those industries, and especially agriculture. And we're very excited because, for example, here you can see on the right, this is on cacao plants in southern Mexico. It's a region that's been going through a lot of volatility. They've been getting floods and they get a lot of drought. And cacao, obviously, it's a very important crop. It's a very important cultural crop for Mexico historically. And so we've been seeing that when we apply our product to these plants, they gain a little bit more resilience against fungi and also increasing yields. So this is just to show that we're very excited about sort of taking something that's created again locally, a problem, and turn it into a local solution. I'll be happy to answer any questions in case that there wasn't anything clear.
Thank you, Jorge. I think we're going to go over to Mar's presentation next, and then we open up again for questions and for discussion. I also just saw that our third speaker, Legina, just signed in. So after Mar, we hear from Legina about what they do with Sargassum in Barbados.
Okay, also if you want to have Legina first, I'm also fine with that.
Let's give her some time just to settle in, I guess.
Okay, cool. Then
thank you, Francesca. Thanks everyone.
You're welcome.
Okay, then here we go. Can you all see my screen?
Mm-hmm. Yes, we can see it.
Cool. Perfect. Okay, so thanks, Fran and Jorge, for setting up this stage. So now I just need to take it up from there. My name is Mar Fernandez Mendez, and I work as a scientist at the Alfred Wegener Institute. But I spent the last 3 years working at Geomar, where I learned a lot about artificial upwelling. And actually, before I was a sea ice algae person, so I went to the Arctic every year, and that's where I did my PhD studies. So I know a lot about the Arctic and all the algae growing there. And that's when I realized that as a scientist, just going to the Arctic every year and seeing how we're basically destroying that ecosystem was not enough. And that's why now I'm moving a bit towards finding solutions. And I came across Sargassum thanks to my professor, Victor Smetacek, and I thought, okay, this is a really cool algae that could actually be part of the solution for climate change. And so now I'm also acting as a scientific advisor for a company called Seafields that is trying to actually make things happen. So I'm going to tell you a bit about why Sargassum could help us in sequestering carbon. So first of all, when Sargassum reaches the coast, it not only causes a problem for tourism and people's health, as we've heard before, but also it destroys many of the ecosystems of the coastal ecosystems that are usually growing there, like mangroves and seagrasses, also coral reefs. And mangroves and seagrasses are active CO2 sinks, so they also absorb carbon. So if they are destroyed, this function of CO2 absorption stops basically. And also, as Jorge mentioned, when the Sargassum gets to the beach, if it's not collected or if it ends on landfills, then it starts emitting CO2. So then it acts as a CO2 emitter. So every patch of sargassum that we manage to prevent from reaching the beach and decomposing there, it's avoided CO2 and methane emissions. So this is a very important point, that anything we can do to prevent that sargassum from reaching the coast is actually already contributing to solve a bit climate change. Now, of course, to create products out of sargassum, you need to have a stable supply of sargassum. And that's why there's some companies that are looking into farming or ranching this sargassum offshore, where you avoid the pressure to the coastal areas, and then part of it, you can sink it for CO2 storage. And this is mostly what I'm going to talk about. Now, first, before I start, why do we need carbon removal? And I think both Ray and Fran already touched a bit on this, but basically, if you see here this gray area, this is reducing CO2 emissions, and we need to do a lot about that. But even if we do a lot about that, there will always be a little bit that we still need to remove from the atmosphere to reach zero emissions, net zero emissions, especially because there are a lot of parts of our economy that are very, very difficult to decarbonize as fast as we need to do it. And that's why we need carbon removal technologies, because there will be always a few gigatons that we don't manage to stop emitting, and we basically need to sequester them to get to zero. And also, if we get there and we actually then want to restore our planet how it was before the Industrial Revolution, which was the safe CO2 concentrations in the atmosphere, then we have to start removing historical CO2 emissions from the atmosphere. So no matter which path we take, we need carbon dioxide removal technologies. Also, it's very important to understand when people talk about conserving forests or blue carbon stocks like mangroves or seagrasses, this is very important, but this is not enough, because we need additionality. We need to sequester more carbon than what we are sequestering at the moment. Okay, so how can sargassum help? Sargassum can help in two different ways. One, through emission avoidance, because if you create products from sargassum that are substituting products that would otherwise be done with fossil fuels, then you're actually avoiding CO2 emissions. So for example, the example that Jorge was talking about, the fertilizer, usually producing fertilizers is a very intensive CO2 process. So if you produce fertilizers from sargassum, which is actually sequestering carbon, this is a huge gain for the climate. Now, the other option is to sink the sargassum. And now, of course, we don't want to sink the sargassum maybe right away, because as we've heard, we can extract a lot of valuable products from it. And also we need to burst all the little bubbles that it has to actually make it sink. So actually, first processing the sargassum and then extracting the valuable products on one hand, and then using the leftovers, which are usually very rich in carbon, because that's the part we don't need. Then if we do that, then we can do the sinking. And here you can see some of the preliminary tests of making one of these bales of sargassum with the shredded material. And you can see how it nicely sinks down to the bottom of the ocean. So this is feasible, it can be done, but there still needs to be a lot of research done in this direction. Now, some scientists have suggested recently that the Great Atlantic Sargassum Belt that Francisca told you about is a great example as a natural analog of what it would be to actually do these macroalgae offshore farms. And it is true that in some ways it's a natural analog, because it's kind of big scale and it has a lot of sargassum growing on a big area. However, there are certain things that don't really apply from the natural Atlantic Sargassum Belt to what these farms would look like. So the one thing that is positive about having already sargassum in this area is that we know that it's not a foreign thing for the deep sea community. So in the benthos, in the abyssal plain, we've already found sargassum sinking naturally. So this would just be enhancing a natural process. You can see it here, sargassum everywhere. Now, what is important to make things right is to think about the location. We cannot just put farms anywhere. We need to think about where we can put them. And Ray already mentioned that going to the subtropical gyres might be a good idea. So those are these areas here, for example, and in the Atlantic, it's this one here. So why would it be reasonable to go to these areas? is mostly for two reasons. A, because right now they are ocean deserts, so not much is growing there. So if we manage to fertilize them, as I will talk about later, then they could turn into productive areas. And second, because they're offshore. So we don't want to put more pressure on coastal ecosystems. We have already a lot of stuff going on the coast, and we don't want to put more pressure there. So we need to move offshore. Now, the second thing is, where do we want to do the sinking? And so it does matter where we do the sinking, because we don't want to put some bales of sargassum on top of a beautiful hydrothermal vent where there's a lot of biodiversity in the deep sea. Of course not. We want to go to those areas of the deep sea that have almost no biology growing there, maybe just some microbes, but not much stuff. And there's a lot in the abyssal plain that looks like that. And also we want to go to areas where we know that the deep waters at 3,000 meters, as you can see here, this is the time that the deep waters stay, or it takes for them to get back to the surface. And so the more yellow it gets, the longer these deep waters will stay there. So for example, the North Pacific would be a great place to do long-term carbon storage for 1,000 years. But the North Atlantic here is also pretty good, up to 700 years of storage. So that would definitely give us enough time to solve our issues with how we produce energy and how we establish our society. But also, this is considering that the organic matter that you're sinking gets remineralized and could therefore come back to the surface. But as Ray mentioned before, we could also take care that some of it is buried in the sediment, and then it would basically never come up again. Okay, and also how to do it right. And again, there are 1,000 ways of doing things wrong, but I think if scientists work together with the engineers and with the people that really want to look for solutions, then we will find the way of doing this in a transparent, sustainable, and controlled way. And so one of the issues is, where do we get the nutrients from? And so the lucky thing is that in the ocean, we don't need to bring fertilizers from land and put them in the ocean. We actually have the nutrients in the deeper waters. They are there, and we can actually bring them up through artificial upwelling. There's some concepts out there, for example, using the salt fountain principle that Ray also knows a lot about, and we can try to bring deep water up without using a lot of energy, because basically you use the density difference to bring the waters up. Then, of course, when we do this and we establish the farms with the artificial upwelling and so on, we need to monitor and control both from the surface, maybe through satellites and drones, but also what happens at the deep sea, at the deposits of bales. So we need cameras, we need sensors, we need to do proper life cycle impact assessments and also environmental impact assessments. And once all of this is in place and we know how to track and monitor this, then we can move forward. Now, if I look a bit into the future, and this is a little bit a futuristic view, this comes from a very forward-looking architect, Bjorn, he's called. And you could imagine even to create like ocean gardens in the middle of the ocean and combine them with producing clean energies like hydrogen, even having tourists going there and spending their holidays offshore, disconnected from life, and trying to have a nice time in contact with nature and with the ocean. So I think this can be a new industry, a new way of seeing things. You can create also food, because you can put you can grow fish and mussels and other things together with the algae. So I think it has a lot of potential, and especially when you compare it with other ways of sequestering carbon in the ocean. I think macroalgae, and specifically Sargassum, they're just fun. It just seems like a nice thing to do and to move forward. Okay, and that's it. And thank you for your attention. And if there are any questions, happy to discuss. Fran, you're muted.
Sorry. Thank you, Mar, for a really interesting presentation. Ligina, are you ready to give a presentation about what you are doing with Sargassum in Barbados?
Oh, hi everyone. Yes, I'm ready to talk. It's exciting to see other presenters and what else is happening. So I can share my slides. Let me just show my slides and then I'll share. Okay. All right. So I had a slight mix up with time, which is why I jumped in just a few minutes ago. I'm sorry about that. All the time zones, I have them modeled in my mind. But today I'm going to talk about a recent IDB technical note that was published in May this year, based on some research we've had in the lab. So my name is Legina Henry. I'm a mechanical engineer. I'm a lecturer for renewable energy at the University of the West Indies in Cave Hill, Barbados. And this study is called the Experimental Evidence on the Use of Biomethane from Rum Distillery Waste and Sargassum Seaweed as an Alternative for Fuel for Transportation in Barbados. So these are my co-authors, and basically my co-authors are students at the University of the West Indies in Cave Hill, Barbados. And we spent some time in summer 2019 looking at biofuel for transportation in general, because Barbados is on a path to 100% renewable energy and fossil fuel free by 2030, which is in just 8 years from now, basically. So we looked at 4 problems in our region, and I know I'm preaching to the choir, so I'll race through the problems because we all know about these problems. So rotten Sargassum seaweed on the coastlines where beach tourism is a big part of the economy, that's a problem. I don't need to explain it, but for example, $120 million was spent throughout the Caribbean region in 2018 clearing beaches, okay? Another problem in Caribbean islands is disposal of rum distillery wastewater, and there's always tension with environmental protection and what happens with rum distillery waste. So this is a big factory product we have in our islands. Another issue is biofuel crops competing with food agriculture in our land-restricted small islands. So having this goal of fossil fuel-free country by 2030 means the question of energy crops comes on the horizon. And of course, we live in small islands, and so land is not freely available to share equitably and happily with food agriculture, and that's an issue. And then I mentioned that Barbados is on this path to being fossil fuel free by 2030, and we've looked at electric vehicles, and about 20 to 25% of the fleet could be electrified by 2030. But certainly not 100%. So biofuels would have to be some part of that solution in there. Looking at 2 bigger trends though, there's this international trend towards the electrification of transport. Let's say 5 decades from now, certainly you wouldn't be able to buy maybe an internal combustion engine car. And so we're looking at small countries like Barbados where energy security would be an issue to electrify road traffic and everything else. So we see this as a potential solution there. Another trend we see is in Barbados, this aggressive push towards solar power. And solar PV has its place, and it's a beautiful technology, a beautiful opportunity. And I teach renewable energy, and I'm a big fan of solar PV. But right now, the electric grid is supported probably almost 100% by fuel oil. And so to have this liquid fuel powered grid and lifestyle and technology and economy, then suddenly powered by solar power 8 years from now, primarily, would be problematic. And especially to me as a mechanical engineer, and when you speak with electrical engineers, this looks problematic for a few reasons. But one practical example I'll give you is this year on April 9th, the La Soufriere volcano erupted in St. Vincent, which is 176 miles west of Barbados. I'm looking at the map in my head, yeah, west. And volcanic ash came across the ocean, and we were covered in ash for 10 days. Barbados was covered in ash from the La Soufriere volcano, and solar PV panels didn't perform for those 10 days. I took cold showers those 10 days because we have solar heaters on our roof. So a dispatchable power system is important in cases of emergencies and in natural disasters, like, for example, the volcanic eruption. And I could give more reasons why you wouldn't want to go from 100% oil powered to 100% solar PV powered. Why you would want to go to another green but fluid fuel. All right, so our story, what's our story? So we started off summer 2019 looking at biofuel feedstocks in Barbados. We thought Brazil was an inspiring picture because they drive something like 2/3 of their traffic drives on biofuel power from sugarcane. And we thought maybe Barbados could be a little tiny Brazil in the Caribbean Sea. Who knows? So I'll tell you, biomethane can cheaply and easily power electric grids, and it could power vehicles. So this is an example of a mid-90s model, sorry, mid-2000s model, the Fiat Tetra fuel. But also right now on sale in Trinidad and Tobago, one island across from Barbados, is the Honda City CNG. So these cars use compressed natural gas to drive. Barbados, I'll tell you, has this nationwide gas grid. And let me just move the panel so I'm seeing you guys, but not seeing my slide. Okay, so now I'm good. Barbados has a nationwide gas grid. And so we have the technology in Barbados for biogas to go to where people live and where they want to fuel up their cars. One more thing I'll say is anaerobic digestion of sargassum to produce this energy is water intensive. It's a 4-stage process starting with hydrolysis, and you need some source of water. Barbados is water scarce. And so my proposal for using rum distillery wastewater, which is available in hundreds of thousands of liters every day, and not used right now, discarded by evaporation or treatment, and then it gets pumped into the ocean. All right, so again, I said we looked at Brazil, and we looked at what the sugar industry in Brazil has looked like in the past 10 years. We had 10 years of data that we could compare Brazil and Barbados, and saw this drop off in the sugarcane industry in Barbados compared to Brazil. But also looking at the whole agriculture sector in Barbados, it seems to be strong apart from sugarcane. So whatever are the pressures, which we kind of looked into, the pressures that allow that sugarcane has been on the decline for 7 decades in Barbados. So it wouldn't be the viable feedstock to drive road traffic here. Okay, so one of my students was on the bus heading home and saw mounds of sargassum on the beach and saw cranes moving it, and thought, why don't we look at it? And I'm sure these authors are familiar to you that say the sargassum supply is steady and stable and expected to be here for a while. And one of the big reasons being, so it comes across the Atlantic. Even Christopher Columbus in the 1500s saw it on the Atlantic Ocean. But why is it here so much now? Since 2010, there's been an uptick because of increased nutrients coming off South America into the ocean and producing these optimal resources for increased sargassum seaweed. So what did our numbers look like in the lab? So we went into the lab with distillery waste from different distilleries around Barbados, and we looked at sargassum seaweed. How does it perform? What kind of methane out per gram of fresh matter? And we had a nice comparison because we worked with Dr. Holder in the chemistry department on this campus. And he found these numbers for the grasses being posed by the government now as biofuel grasses. And he found that the numbers for biofuel grasses on day 11 look like something like 50 normal milliliters of methane, per gram of fresh matter. When we looked at sargassum with rum distillery waste on day 11, we got near to 60, between 60 and 70 for our optimal mixes of gas out per gram of fresh matter. So what is it? Our market looks like right now every year 134,600. Well, there's 134,600 registered vehicles in Barbados. Small market is a tiny island, and they need to be shifted away from fossil fuels in 8.5 years. Most Bajans live around the nationwide gas network that is built where the population lives. And the electric vehicle idea will probably work for about 1/5 of the population, but not more. So we have a decent market in terms of who will need to convert their cars to CNG and drive them on biomethane. From the results we got in the lab, we did some calculations we did some calculations on the lab results, but also using some open data about what energy does this transport sector in Barbados use. And our calculations look like we'll need something like 600,000 liters. So 600 million liters or 600,000 meter cube of wastewater And optimally, it would be rum distillery wastewater, but we could supplement it with city waste treated. But about 100,000 tons of fresh sargassum in a year. In 2017, and I just showed this map of what the exclusive economic zone of Barbados looks like. It's huge. Barbados is 465 times more water than land. Barbados, if you look at Barbados in terms of the exclusive economic zone, I mean, we think of it as this tiny little island, a little dot on the map, but it's comparable to, say, a small country in Europe. Like Switzerland. Barbados is 4.5 times the size of Switzerland if you look at it from the standpoint of the entire exclusive economic zone. Okay, so in 2017, 20,000 tons of Sargassum seaweed came through the Atlantic, the Central Atlantic and the Caribbean Sea. So we think enough of that would be in the exclusive economic zone of Barbados that you'll cover your 10,000 in that exclusive economic zone. The question is the logistics of getting Sargassum from all here to that tiny dot, and that in itself will be a task, a fun task for engineers to solve. Do we have hurdles? The exclusive, like I said, we have more water than land, and so the idea of Sargassum being this economic entity is something that needs to be regulated, and that's a hurdle we need to go through in the next 8.5 years as we develop this solution. And then I thought, in terms of what we were looking at, we've started at Caveville with this 2-car pilot where we've converted, the plan is to convert my car and one other car on campus to be driving on Sargassum seaweed. This what I call my 2-car pilot was funded by Blue Chip Foundation in New York, a grant from them. And so we are in the stage of procurement and things, different parts of this pilot being shipped to Barbados now. And our next hooped pilots will go up to between a couple hundred cars, where we'll convert cars from different entities around the government of Barbados and drive them and get data on cars driving on Sargassum. And that we expect that pilot to happen from next April for 12 months. And then that dream is to start moving towards like actual portions of road traffic in this country. And so that is my solution, I believe. I believe that was my last slide. Yep. So thanks everyone for your attention.
Thank you, Legina. That was really interesting. And I love how Barbados is kind of one of the world leaders in actually saying you're going fossil fuel free and has really ambitious goals compared to some of the Western countries. And the really cool solution you have to actually make this happen. So now we've heard a bit of the more positive stories of how the ocean can help us with climate change. And I want to open the floor up again for questions and comments and discussion.
This is a question from Mar. I'm wondering about the open ocean farming of Sargassum, given that Sargassum is a bit of a nuisance in the Caribbean. There may be people who are opposed to producing more of it by fertilization. And I wonder if you know about this body called the Sargasso Sea Commission that's headquartered in Bermuda. And they're devoted to preserving the Sargasso Sea. And I was wondering if they had taken a position on open ocean Sargassum farming.
That's a very good point, Ray. They haven't taken any public positioning yet, but I think, again, it's about how you do things. So of course, the message needs to be clear that the Sargasso Sea needs to be protected because that's a unique ecosystem. And so we don't want to use the resources of the Sargasso Sea. That's why we want to create Sargassum elsewhere. And also that we have to do it in a way that is controlled. And that's why I was talking about monitoring with drones and satellite to make sure that the Sargassum that we grow extra in the subtropical gyres doesn't escape the farms or the subtropical gyres. I mean, the chances I think would be pretty low, because if you think you're in the middle of the desert and you have these farms with the artificial upwelling, if there would be some Sargassum going out for any reason, I would think it would either stay in the gyre anyways, or die because it doesn't have any nutrients. But of course, we need to check that. I mean, I'm not saying that this is a straightforward thing. And I think the only way to move forward is to make sure that all these things are taken care of course. We don't want to create more problems by trying to implement the solutions.
Mm-hmm. And the Sargasso Sea Commission is mostly focused on the Sargasso Sea, and that nothing happens to that specific area of international waters. And it doesn't really have any say or influence, or doesn't really interfere with, for example, the sargassum that's now in the Great Atlantic Sargassum Belt we talked about. So they're quite different things, and one of them is causing a problem while the other one is called the rainforest of the sea. So there's very different ways of dealing with the two of them as well.
Have there been many experiments in sinking sargassum in bales to the bottom of the ocean?
Not yet. We're right at the beginning. I know that Fearless Fund is working on similar stuff, and then the challenge is always to get the funding to fund the deep sea research. The bailing and the sinking is not the problem. Is doing all the monitoring at the deep sea that is the challenging part to get funded. But I think there's good advancements in that direction. Yeah.
Yes, and there's a company called SOS Carbon, which did some sinking through pumps near the Dominican Republic, but without any monitoring of the deep sea. They just tested out the engineering option of if it's possible to sink it by pumping it down to about 100, 200 meters where the bubbles will pop and it will sink on its own.
Sure.
Okay, great. So I was wondering about the resilience of using this sargassum as a fuel. It sounds like an ingenious idea. Is there any problem that there's like a seasonal cycle to when it's available, or if it was a particularly, I don't know, warm year, would that have a negative impact that would make it less reliable as a fuel?
Yeah, thanks for your question. So I think Ma mentioned the idea of farming the sargassum if it becomes this economic substrate for energy, that we look at some of the technologies which have been around. I think I even saw a patent written in 2008 for farming sargassum on the surface of the ocean in a controlled manner. We're in the stage of piloting now. So we're in the pilot phase now, where we're really proving concept. So proving that you could actually do that whole chain from fresh sargassum in the ocean and the other substrates to drive in a car. The technology already exists. We're not inventing any new technology, but it's just what we're putting together is unique. And the idea of the logistics of getting sargassum to where we're going to produce the fuel is a big part of it. And one part of the logistical question is, what is the how certain will we be of supply? And so that's part of the work that we're doing at the university right now.
So Alison, you just joined us, and I was just going to recap the question that Ray mentioned before, because maybe you can answer better than me. He was asking if there are already any running trials on the deep sea impacts of sinking sargassum. I said from my side, not yet, but maybe you know if there's anything already going on or starting soon.
Yeah, thanks for the question. Hi, everybody. I feel like I came in at the end of the meeting, but sorry about that. Wasn't sure it was my meeting or not. Yes, we did a sinking test in last January, February, and we don't have the results back from that, but we hope to get them in probably December of this year. So it's a very simple test. We didn't have the budget for a lot of sensors and whatnot. Anyway, so I don't have anything to report, but just to say that it's been in the water for, you know, whatever, 8 or 9 months now. And we hope to get some basic response. Anyway, good to see everybody.
Yeah, we were discussing that it's always difficult to get the funding to actually do the deep sea side of things, right? Like the bailing and the sinking, it is maybe not the most difficult part, even though of course it also requires some budget, but actually to do all the monitoring and measurements down there, that's the tricky part.
I would say it's probably all tricky, but every team can probably put in, easily take care of one or two of the steps, but not all of the steps. So that's where it becomes a challenge. So, I think everybody needs to get together and talk about this and put their, one resource, two resources together, and then we can do it. But anyway, we are doing what we can in the way that we can and in a very low budget way.
Exactly.
So for, I don't know if y'all know what we're doing. Basically, we run a project for the U.S. Department of Energy, RPE. It's part of the Mariner program. And the goal of that is to produce macroalgae at energy scale. But we also see that as carbon dioxide removal scale. I haven't seen a really great analysis on what's the best direction to send that biomass. So if anybody has seen that kind of analysis, I would love to see it and talk about it with you. Anyway, hi and thanks.
Yeah, I think we're still all working on figuring out what can be done with the biomass. And then at one point we have to compare the different products to see what makes sense and what can be combined with each other. Because often you can make multiple products out of the sargassum and then maybe sink the rest of it. But I think what Mara and Alison just said now is one of those other hurdles that the oceans are facing, is that in terms of climate and climate solutions, there's actually very little money going towards ocean solutions, and they're very little talked about. So, which also ends up in less money going there because nobody knows about it. So yeah, unfortunately, very little money goes towards these really cool ideas that could potentially help us, which makes it harder to really get them moving forward and get them to a place where we can do pilots and then afterwards scale up if it works out well as a pilot.
Yeah, I think, Alison, in order to give you like an idea of like the few little things that we discovered recently, it was mostly that if you don't burst the bubbles, it won't sink. I mean, I think we all knew that, but just the fact of mechanically pressing it together will not burst the bubbles. You really need to shred it. And that's why we came up with the idea of, okay, then if we have to shred it anyways, then, like Sea Combinator is doing, then why not extract first everything we need out of it and then only sink the excess, the waste product that is anyways rich in carbon. So that's seems to be kind of the direction to go. But then the other thing that I think is not solved yet is how to sink it, because it doesn't stay together as a bale, like at least not with a regular mechanical press for putting it together, So if you start wrapping it in some material, then which material do you use? You need to start sinking some net or something. And if you do it the SOS carbon way, which is just, putting a tube and putting it down to 100 meters, is 100 meters enough so that it actually sinks down to 3,000 and then it stays there? Probably not. So these are all the things that we're still working on. And I think what you said, we need to collaborate so that we don't double efforts and don't, repeat things, but rather all of us work in the same direction to make things in the best way possible.
Yeah, Mara, I think those are some really good points. I think of wholesale sinking of biomass as it is not feasible today. So we're running the test because we can and because the scientific community needs the information. But I don't anticipate that that's the way it's going to go unless the price of carbon, ends up at 300 or more. It's not going to be feasible. So. And meanwhile, we have an economy that needs raw material in a better way than that provided by fossil fuels. And fossil fuel rich growing processes, fertilizers, et cetera. So I think there's a way to do this. It's just, we kind of need to, flesh it out and decide, I think of it in terms of, let's find the highest value uses for some of the biomass just to get started. And then we'll figure it out along the way as we scale. We don't need that highest value product stream. And, there will be different ways of conducting a company at different scales. But the main thing is, to try and get started. Yeah, anyway, for what it's worth. We're still in R&D, we're not commercial. So I'm sort of talking to myself, but that's the way I see it. And so I'm just sharing it and how we're doing what we're doing. We're syncing it because we need the information. One day we may need to sync it all fast, as fast as we can produce it.
I have a question about the people processing sargassum. Do you separate the animals living in the weed before you process it, or do they just get ground up with the sargassum? Here on Cape Cod, we often gather eelgrass washed up on the beach and put it on our gardens to fertilize. And you can still find amphipods hopping around in the eelgrass 6 months later. So I'm just wondering what happens to all the little sargasso fish and whatnot that are living in the weed.
Well, I'll jump in here. We haven't done a big, large scale collection, but in the collection we've done so far has been all manual and a bunch of grad students. So my students actually separate out the little tiny turtles from but they catch it on the water. So we don't take the ones on the beach. We take deep water. Not washed up. So still floating sargassum, and any little tiny turtles, they pull it out. It's not a lot though. Then I've spoken with people from, Francesca, you just mentioned the company Andreas Bolseros, who has a harvester. I forgot the name of the company, but
SOS Carbon.
SOS Carbon. So they've said they haven't had a lot of bycatch with their device, which picks it up with nets on the water surface. Well, that was the device I was interested in. They also have this other thing where they suction sargassum, but the one I was interested in is their nets that ride the surface of the waves from a little fishing pirogue. You could collect the sargassum, and bycatch is minimal or zero.
Yes, and I know from researchers here in Mexico that when the conveyor belt boats were developed here in Mexico to take sargassum out of the water, they worked with biologists at the university to make sure there's very little bycatch and that they make the conveyor belt in a way that it doesn't, like, bycatch is avoided. And also the people on the boat are trained to see the animals and actually pick them out. So there's very little bycatch. First of all, because a lot of the animals don't even get close to the shore. They leave the sargassum before. They kind of, I guess, know that, okay, we're getting somewhere close to shore. I'm gonna go to a patch that keeps on going, that keeps on living. Because once the sargassum actually hits the shore and the beach, if it's not picked up by a boat, then all those animals stay on the beach there too, and they get eaten by birds, so they're just rotting on the shore, which is unfortunate fate as well. James just mentioned we are getting up to the 2-hour mark, and as most of the conversation has moved towards people looking into collaborating with each other, I would suggest we stop the recording now, and anybody who wants to stay on and keep talking can keep talking, unless we have other pressing questions for our guests that spoke today.